want to talk to you about why it's important to have the correct static pressure and CFMs in a duct system. Well, we're back at it again. Alright, so you just got a duct system installed in your house, or you are getting ready to design a duct system, or you have a system that's just not working like it should. Well, what do you do? So I was, again, on that YouTube, and the good thing about YouTube is there's a lot of information out there. The bad thing about YouTube is there's a lot of information out there, and it's not all right. So, here we are. We're talking about ductwork again. Now, I want to talk about a specific video that I came across on the YouTube. And they're talking about designing a duct system in a house. So, I'm going to pull it up here. Let me see. There we are. Now, this particular duct system, okay, was installed by somebody. And I don't know much about this system. So, I can't. You know, we're going to assume a lot of things, which you should never do, but we are going to kind of reverse engineer what is going on in here and see if we can figure out if this system is going to work or not. So, what we've got is we have a 3-ton air handling unit. We do not know if this is a heat pump. We don't know if it has electric backup. We don't know if it's straight air conditioning. We don't know what brand, what what the width is of this unit. We don't know anything other than it's 3-ton. There's a 3-ton blower there. Aside from that, that's all we know. So, the thing with air handlers is that they generally will come with a static pressure associated with them. So, air handlers, unlike furnaces, air handlers take into account the actual evaporator coil and everything internal to that unit, whereas furnaces don't take into account evaporator coils. So air handlers will have a pressure rating of somewhere around 1/2 inch, okay? And so I'm going to work with this system based on that. It's 1/2 inch. With that though, I do not know if we have electric backup heat on here or anything like that, so I have not taken that into consideration. I did not use any electric backup heat coils in calculating anything because well, his good drawing here doesn't show any, so we're going to assume that there is no heat in this house. So, moving forward, we've got a 3-ton unit. It's pushing air into what looks like about 12 feet of duct trunk. I'm assuming this is duct board just by looking at the system, because what we've got is, I like to call these rat's nests, but there is actually a name for this type of duct system, and I have yet to find one here in Pennsylvania, and it's probably for good. We don't see them a lot around here. I've run into a few of these in my entire life, and they give you problems. But anyway, if you look at this, what we've got is we've got some flexes coming off of a main trunk, feeding a triangular type of duct box, feeding more flex, going to what I'm assuming is a 10x10 ceiling diffuser here, here, and here. And then also up top here, we've got what might be a sidewall register. And, I really don't know. We don't know what this guy's doing. But we do know he's got one return right here in the hallway. We've got a central return, likely in the ceiling of this hallway, and a big 18-inch flex feeding that baby right there. Is this system going to work? Well, that's a good question. The guy who is installing this was using a train ductulator. Okay, now the train ductulators are very similar to all the other ones in that they can figure out dimensional duct based on friction rates and velocities. His ductulator looks very similar to this one. Okay, it's got a wheel that spins around the center, and you can base your ductwork off of what CFM you're trying to push. The nice thing about this one, opposed to the one that he had, was that it actually is for flex duct, okay? This one here is cheap and is plentiful. And as a matter of fact, if you want one, I have a few in my trash can. But we're going to look at this one here. One thing I do like about this calculator is whoever designed it knows that flex duct is very, very seldom installed correctly. So what we're looking at here is we will look at our volume versus our friction loss. We will come up with some rectangular duct, okay, over here on the side of it. And up top here, we've got the ability to read round duct. But it says right there, steel duct diameter. This is for steel, smooth steel duct. But as we look here, you can also do flex duct. The nice thing with this calculator is it takes into account compression rates. So 9 times out of 10, it is very probable that your installers are not actually installing flex duct the way it's supposed to be. They're not. You don't have two guys stretching that flex duct out for 60 seconds and then installing it in nice, short, straight lengths. Okay? The likelihood that that is happening is very slim. So this duct calculator takes into account compression. Okay? We've got 3 different categories here. We've got a 4% compression, a 15% compression, and then a 30% compression on the bottom. If your guys are not stretching their ductwork out straight, if they're putting any bends in it, sags in the support system, anything like that, I would generally use the 15 or most often the 30% compression. Now, let me give you an idea of what this looks like. So, 6-inch, okay, 6-inch round. How many CFM can you get through a 6-inch round? Well, we all know that you can get 120 CFM through a 6-inch round, right? Well, that's because we are all sizing it at 0.1 friction rate, which we know doesn't work because you watched my last video. 0.1 doesn't work all the time. Sometimes it does, but let's just, for sake of argument, say that we are designing our system at 0.1 and we are squeezing 120 CFM through a round steel duct. Great. What does that mean for flex duct? Okay. Well, if it has 4% compression, which means that a 7-inch, or I'm sorry, a 10-foot section of it is compressed to 9.6 feet. Okay, that's not a lot of compression. But what that means is let's see here, a 6-inch would only get us about 65 CFM. Think about that. 65 CFM is all you're getting out of that, all things equal. Now, if we wanted to maintain that 120 through that run, what would we have to do? Well, we'd have to bump it up to a 7-inch flex if we were at 4% compression. If we were at 15% compression, you're over an 8-inch flex, okay? And then if we go down to 30% compression, you're going to have to bump it up to a 10-inch flex. 10-inch flex, okay, to deliver 120 CFM. That's fine. We'll run a 10-inch flex. Well, there's some problems there. If you are running a 10-inch flex, think about this. If you're running a 10-inch flex and you're only needing 120 CFM to a room, like let's say we've got a 10 by 10 room, okay, not a lot of heat loss, not a lot of gain, and we need 120 CFM in that room. So we would probably put like a 6 by 6 ceiling diffuser in that room. Well, what manufacturer manufactures a 6 by 6 ceiling diffuser with a 10-inch collar on it? I don't know. I don't think anybody does. So that's the problem with flex, and that's something you really got to take into consideration. So unless your guys are using steel, insulated steel, or they are actually installing it correctly and putting like a 7-inch, because you can get a 7-inch collar on a 6 by 6 ceiling diffuser. that's you know, that's the end of it. But okay, so let's go back to our example here. Now we're looking at this this system here. Now we've got our very first one coming off here is a 10-inch flex feeding a box of some sort, which is feeding two 8x8s, feeding 10x10 ceiling diffusers in what I believe is probably like the living room area, living room / dining room. Just looking at the layout of the house, I would assume this upper left-hand corner is a kitchen, and then we've got a dining room, living room area, this L-shaped. We've got a hallway here, another hallway, bedrooms all against this right-hand side of the house, and then maybe like a bathroom and walk-in closets, something like that here. Or it might be a master bath and another like common bath. But if we go back and we're trying to figure out our friction rate for a house, how do we determine how we're sizing our ductwork? Very first thing we got to do is give us a rough layout of where our ductwork is physically able to run, and then we need to figure out where our critical paths are, our critical supply and our critical return. Now on this particular model here, my critical supply, the longest run from the face of that blower, so from that blower, what is the longest run that air has to travel? It is probably either this far master bedroom or this right here, this kitchen. Okay, this 10x6 on this kitchen. So that's for our supply. On our return, well, this guy, he uses central returns, so nice and easy. We come right off the back of the unit. We wrap this 18-inch flex right over to our 20x24 return filter grill up in the ceiling. Done. Okay, all we have to do is get a simple measurement, and we've got our critical path on our return. Excellent. So we add all this up. We add the length of this flex minus any loss in the actual fitting here on the return. We do the same for our supply. We add all of the straight lengths up. Any losses in fitting. So if we've got a 90, we've got to add so many equivalent feet for that. I have another video on how to determine that. For this one here, this one actually wasn't too terribly bad. I came up with a total effective length of somewhere around 250 to 300 feet, okay? Again, I don't know the actual lengths and dimensions of this building, but based off of his drawing and kind of approximate sizes of rooms, I'm going to assume that the total effective length for this design is somewhere around 300 feet. We have figured out what our total effective length is. Now, we go back to our air handler unit. Let's just say we go in the manufacturer's log or data book, we figure out that our air handler has a pressure rating of 0.5 inches. That's a good average for an air handler. Then we start taking off any pressure drops for anything in our airstream. So where are we going to hit a pressure drop first? Well, you would probably hit one on a resistive coil if it was a heat pump like electric backup. We don't have that here, so I'm not even including that. Dampers, okay? If you've got dampers in the section, I don't know if this guy puts dampers in, but you should put a damper in, especially on a system like this, because these flex units these flex systems like this are so hard to balance. You'd almost have to have dampers in. So we're going to have a damper here. A damper will generally have a pressure drop of a 0.03. We move on. What's our next thing that we're going to hit? If you have any other dampers, fire dampers, anything like that, you might add them in the equation. But our ceiling diffusers themselves, okay, they have a pressure drop associated with them. If you're using a software, you may or may not have the ability to change the actual ceiling diffuser pressure drops, or they may have a generic catalog of pressure drops associated with specific registers, grills, and ceiling diffusers. Now, what I do is I've got books from Hart and Cooley. Okay, this is my local distributor. They have Hart and Cooley products, so in this book I can go through and determine what the pressure drop is of any floor register, sidewall register, grill, ceiling diffuser, whatever. It's all in here. There's a commercial version of this book and a residential version of that book. So let's just say we are using an actual 10x10. I'm going to go off of what this guy has, a 10x10 ceiling diffuser. We take that ceiling diffuser, we look it up in the book, and we find that a 4-way ceiling diffuser, 10x10, has a pressure drop of a 0.031. Okay, so then we add that into the equation. So now we're at the air handler, 0.5, minus the 0.03 on the damper, minus our sealing diffusers at a 0.031. Okay, so that is our supply side pressure drop. Okay, now we're going to look at the return. There is a pressure drop associated with this filter grill itself. Again, you'll go right back in that book and you'll try to figure out which 20 by 24 filter grill you're using. What is the drop associated with the grill itself? And you will add that into the equation. Okay. For this one, I found a 20 by 24 ceiling filter grill or filter rack at a 0.09. And then what's right behind that? Well, the filter itself. The drawback to a lot of these is you're limited to a 1-inch filter. So we're going to use just a standard 0.1 for the drop on that. So we'll take that 0.1, we'll add it into our equation, and we will come up with our available static pressure. In this example, my available static pressure is 0.249 is my available static pressure. So then what do? Well, we are going to multiply that times 100. Then we are going to divide that by our total effective length. I'm going to use 300 in this example. And that will give us our friction rate that we are to design this system on. It is a 0.083 friction rate. So that is what we're actually going to size all of our ductwork on. Now, here's the thing. I went through and I kind of looked at his whole setup. These 22 by 12 main trunk sections are not too terribly bad. I mean, they're slightly high, like large on the volume side. Our velocity is not really high, but that's fine. If my velocity is really low, I don't care. As long as it's not high, I'm fine with that. I'm not going to beat them up over the trunks themselves. But where I have an issue is looking at this critical path here. We've got a 10-inch flex that's kind of snaked through the attic is what it looks like, feeding a 10 by 10 box. Then off of that 10 by 10 box, we have a 7-inch flex feeding, I'm just going to assume that it is a sidewall register. Okay? Now, when we are looking at that, a 10-inch flex at 4%, the most we are going to get through this 10-inch flex is somewhere between 175 and 300 CFM. Because remember, we have to account for this 10-inch flex, this 10-inch flex, this 8-inch, this 7-inch, this 7-inch, and this 5-inch. The guy that was installing this, or designing it, did not, he said that this 5-inch here was free. That was free CFM, okay? Well, guess what? There's nothing that's free. Nothing is free, not even air. So we have to take that into account. This 5-inch right here is stealing air from this whole system. We have to account for that. So anyway, given all of that, this 10-inch right here is going to give us a 300 CFM at best if it's only at 4% compression. Considering no, it's not snaked around anything. If it is, if there is any snaking here, if it's being bent in any way, shape, or form, it is not a short, straight run, we are going to get somewhere between 120 and 175 CFM through this run. So let's just say we've got 175 CFM hitting this box. Now we're going to take 175 CFM. We are going to divide that between 4 diffusers. We've got a 5-inch, a 5-inch, an 8-inch, and then a 7-inch. I guarantee most of that air is going to hit this 8-inch right here, and there will not be a whole heck of a lot left for this 7-inch guy here or any of these 5-inchers. So we're going to take that 175, we're going to divide it across those 4, and then we're going to get, maybe, let's just see, 40 to 60 CFM out of this one. I would be happy. Well, I shouldn't say that. I shouldn't say I'd be happy. I'd be pretty upset. I'd be pretty pissed off if I was this homeowner. And I was only getting 45 to 50, maybe 60 CFM into this kitchen. That's not going to work. That is just not going to work. So we've got 60 CFM here. You might get another 60 there, 40 and 40, and and then you just keep going across this whole house. You're going to get kind of what this guy has designed. This system is going to work as he has designed it. and that's what you're going to be left with. Now, not only are you going to have low CFM, but your velocities in these trunks here, or I'm sorry, these branch ducts are going to be really low as well. Like I said earlier, I'm not terribly concerned with low velocity in the duct itself, okay? Where I do not want low velocity, though, is at the diffuser. All of these diffusers need a certain amount of velocity to get that air to disperse in the pattern that is designed to disperse in, okay? If you're not feeding, let's say this 10 by 10 supply over here in the living room, if you're not feeding that with 600 feet per minute, you're not going to get the 8-inch throw that it is designed at, okay? You might get 3 feet of throw. Likewise with the kitchen. It looks like this kitchen, he's got it just kind of sitting here on this wall, and he's throwing the air across the kitchen against the far wall. Well, if you've only got 60 CFM hitting that at a extremely low velocity, let's see what that would be. A 7-inch, yeah, you probably get about 50 CFM. Our velocity would probably be somewhere under 400 at that point. If it's even that high, I don't even know if it would be that high. So then you've got 400 feet per minute hitting that diffuser. You might get 3 feet of throw, maybe 4 feet of throw coming out of that sidewall diffuser. Your ceiling, if you have a sidewall diffuser or even a ceiling diffuser, that ceiling diffuser has to be able to throw air against the boundary wall, which would be your exterior wall or whatever is the boundary of condition. So you would have to then take that upper kitchen supply and move it within 3 feet of that wall. But now what happens there is that increases our total effective length. So as soon as we increase our total effective length, now we got to go back to the drawing board, okay, and recreate the entire duct system based on a larger total effective length, okay, which is going to change our friction rates, which means it's going to change the overall size of these duct runs. So, we're, maybe 20 minutes into this video, and I'm seeing some big problems here, okay? But, it's taking that extra little bit of time to make sure you do it now than to spend a week in this house laying this whole system out, installing it, and then to say, oh, man, it's not working. What do we do now? So what I've done now, we're going to look at something else here, is I've just taken this system, I put it into the computer, and we're going to look at this. How would we change this? How would we do it a little bit differently? Well, this is the layout of the house. This is what I used for figuring out my effective lengths, and this is what I've come up with. Now, what I would probably have done, as opposed to putting a horizontal air handler either up in the garage roof or in the actual ceiling or the roof line of the house, I would probably put the equipment down in the garage itself. That way you can actually maintenance this thing, okay? You can work on it, because nobody likes to crawl up in an attic when it's 130 degrees and try to work on something that is squeezed in between rafters and 3 feet of insulation. So this is where I would stick it. I would stick it down here in the garage. You would lose about 2 feet of the corner, but hey, so be it. The only thing to consider here was whenever you're doing this, you will very likely have to put your fire dampers in so that you're not, the likelihood of flame spread is decreased. But yeah, if you just put a fire damper in the supply and return, you'll be safe there. So, what did we do? We've got our supply in red and our return in blue. Now, what you'll see is as we open this up, I have colored my critical paths with the red and the blue. So, we're gonna bring our ductwork up here, and let me see here. Ran out of space. There we are. All right. Okay, so here is what we've got. We're going to bring our supply up and we are going to shoot it straight down the center of this building. Doing this, okay, running our supply right down the center of our building will keep these duct runs as short and straight as we can possibly get, okay? We're not snaking 30 feet of flex in this direction to a box and then snaking it back over in the other direction to another box. You know, we're going to keep things as short and straight as we possibly can. So if you're using flex, this will be great. If you're using insulated steel, this will even be better. So I have colored my critical path, the furthest supply from my system, in red, okay, which happens to still be that kitchen up in the upper right-hand corner. Or I'm sorry, the upper left-hand corner. So this is our critical path on the supply. Our return critical path, notice we have individual returns here, is this middle bedroom. Our middle bedroom is going to have the furthest return. It will come up across into a main trunk and then back down to the unit. Now, setting the system up this way will give us great airflow. It'll give us the ability to correctly damper everything off and balance everything, and will give us a system that will last a very long time. It'll keep our pressures within the system relatively low, and the static pressures within check for the blower, and keep our air flowing in the way it should be flowing. So that's how we would do that. All of my diffusers, you could use even like the AirTech MV4s or MV3s, depending on which room you're in, and still get the throw that you need to get against these exterior walls without any sort of a problem. So that's that, guys. If you have any questions, let me know. I'm probably going to go over a few more videos like this. I've had a lot of people send private messages and reach out saying that they want me to do like a 2,000 square foot model home, manual J, load calculation, the ductwork, and then equipment selection. So that's probably something that'll be coming up in the pipeline. But so this is how we would do it. Okay. Now, in closing statement, the guy who designed the original system in the video that I'm referencing, he did say one thing that I agree with. He said that if the static pressure is not correct, or you have the correct duct design, what happens? The unit runs, it can't breathe, it can't blow out air, you'll have high amp draws on your compressor, your suction pressures are high, your liquid line side is very high, it causes the unit to run longer and shortens the life of the equipment. The air handler will sweat, you'll have lots of issues. And you are right, my friend, you will have lots of issues. If you do not do this right, you will have lots of issues and your equipment will not last, okay? As far as the other things you said in there, well, you haven't been on the service van very long. If you have problems with low airflow, your suction pressures will not be very high. In fact, they will be extremely low. Okay, you might have sweating. Okay, if your air handler is in an unconditioned area and you're getting condensation forming, but that's because your evaporator is a block of ice and everything's cold. It's gonna sweat. So I agree with you there, buddy. But that's that. You will have lots of issues. So, all right, guys, I gotta go make some money today. So if you have any questions, like I said, reach out to me. We're gonna make some more videos. I've been away from the computer for too long, and I got a lot of people asking me some specific questions on ductwork sizing, equipment selection, and things like that. So we'll see you on the next one. Take care, guys.